All right. Yeah, I think it's time to get started. So, welcome everyone to the third lecture of the NLG course. So, this is the third and the final lecture of the lecture part. So, from next week, we'll be starting the seminar sessions. And today, we're going to be talking about how do you bring these NLG models into practice. So, let you build your model, but how do you productionize it or deploy it in production? And this is, of course, a very broad topic, but we're going to be talking about few aspects related to this, which I've found important in my own work. Okay, so today, more specifically, the aspects that we're going to be discussing are data collection, how do you evaluate your NLG models, how do you optimize the inference speed so that you can run these in real time for some latency critical applications. Another very important aspect is how do you mitigate hallucinations, make sure that your models produce factual outputs. And finally, what are some of the ethical considerations around NLG models? And now all of these topics could be their own lecture or would deserve their own lecture, but so we'll be obviously just scratching the surface, but I'll try to highlight sort of the main points and as well as providing you some pointers if you're interested. So there are many links in the slides to papers that you can look into more closely. But so let's start with the data collection. And I have to say, like in practice, this is one aspect that, at least in my own work, I end up spending a lot of time just making sure that we have enough data and enough high quality data. So, and if we make very rough generalizations, like one thing that's maybe a bit different, at least in my own experience between academia and industry, is that in academia, often, especially if you work in sort of hardcore machine learning, your data sets are kind of given already. So you use some standard benchmark, it has been cleaned and pre-processed nicely. So you just feed it to your model. And then your focus will be more on developing the model and making sure that you can improve on this benchmark over what others have achieved before. While in industry, you kind of, it's common that you would use some existing model that's already been kind of vetted and made production ready. And the focus would be more on curating high quality training data for this model. Now, of course, many of the methods we've discussed in this course, they've been developed in the industry. And also there's a lot of work going on in data collection in the academia. So this is not a clear boundary, but just kind of some emphasis that there is. And okay, so how do you go about collecting the data? I'm going to be mentioning four different approaches. So the first one is basically a recap from the last week, what we talked about then. And so often, like machine learning methods, like you train them with millions of training examples. But we saw last week that if you do a lot of pre-training, you don't necessarily need so much like high quality code data or parallel data. So one important thing to do is to do a lot of pre-training so you can avoid some of this fine-tuning data collection, which can be very tricky and expensive. So how do you do the self-supervised pre-training? We talked about a few different objectives. So the common ones are the masked language modeling task, something that BERT does and T5 does. And then there's the prefix language modeling task which is kind of similar, but you just continue from a prefix that's been given to the model. And these are two very effective pre-training methods. But then there are also some methods that have been tailored to the downstream task that you're actually interested in solving. And some papers have shown that if you tailor the pre-training, also it can give you even better fine-tuning performance. So for example, there's some work for summarization. We also published a paper last year on grammatical error correction and did some pre-training specific to that task. And another way to tailor your pre-training is that you can use maybe one of the standard tasks like the masked language modeling task, but you can tailor the pre-training corpus you apply this unsupervised or self-supervised pre-training on. So for instance, there's a wide number of different pre-trained BERT models that have been pre-trained on some domain-specific data. So for example, you might have some patient BERT model trained on patient records, which will be useful then for some medical purposes. Okay, yeah, so this is the first approach. Then another one, and I think this is maybe I would say this is one of the main approaches. So this is called back translation. As the name suggests, it has been originally proposed for machine translation. And here the idea is that rather than going from the source domain to the target domain, assuming you have some data from the target domain, you can go the other way around in order to create parallel examples. So let's say you want to train a machine translation system to translate English to Finnish. Now what you can do is that assume you have some parallel data already. Now you train a model in the reverse direction to go from Finnish to English, and then you apply this model on some Finnish sentences to create sort of the synthetic English source sentences. And now, although this has been developed for machine translation, this is a very useful concept also in other areas. Intuition behind why this might be a good idea to do is that usually the noise on the source side may not hurt as much as target side noise. And the reason is that kind of when your target is clean, it will teach your decoder to produce fluent outputs. While if you have some kind of noisy, unrealistic sources, this might also hurt, but it might not hurt as much because then it just trains the model to translate something that's not really a realistic output. But as long as it also sees the realistic, the realistic inputs, it should learn to translate them as well. And kind of the concept of back translation, sort of how it's usually understood, is that like I said, you have some existing parallel data, you train a model in the reverse direction, and then you apply it to some target side corpus. But now you can take this concept more broadly also, and interestingly, in some applications, going from the target side to the source side is actually much easier. And a very good example of this is the task of grammatical error correction. So you can imagine that it's much easier to break a sentence than to make it grammatical. You can do the breaking simply, for example, by perturbing characters, words, or word forms. But of course, usually the more realistic the errors that you introduce, the better the performance will be. So this is something that's going to be relevant also for your project works. And just to mention another example from my own work, so as I mentioned last week, we studied the problem of sentence fusion quite extensively, and there we also found that it's easier to break a long sentence into two individual sentences than it is to fuse two sentences. And we used some dependency parsing to do this. Okay, so that's about back translation. The next concept is self-training, and this is kind of a bit, at least to me, it was quite counterintuitive that why should this work in the first place. But the idea here is that assume you have some parallel data set, and then you have some unlabeled or non-parallel examples from the source side. So in the last example, we were talking about target side, but now we have source side examples. And the idea is that you train your model on the parallel data, then you apply the model on the unlabeled source examples to create targets for these, and these give you a pseudo-parallel dataset S. And now the idea is that if you train your model using both the labeled and the new pseudo-parallel dataset, at least in some cases, it actually performs better than just using the labeled dataset. So why this is kind of surprising is that basically you're not feeding any new information to the model, although you are feeding it possibly new source examples. So at least it will expose the model to a wider range of source side examples. But still, it's a bit surprising that this would work in the first place. But this has been shown in many different applications, not just for um, NLG, but also for classification tasks, that often this brings some improvements. And I've also seen it in my own work. Maybe more surprising variant of this is that sometimes even if you just take your original parallel dataset and you just relabel the dataset, so you produce new targets, you discard the original cold targets and you just take the model predictions and then retrain the model. Sometimes even this performs better than the original model. Now, one explanation for this might be that if your original dataset is very noisy, once you train your model, it sort of smooths out some of the noise and it makes the task a bit easier. So I think it's some kind of a sort of regularization that's happening here, why it might be helping. But this is something, I don't know if it's very well understood why this works, but it's a very easy trick to try out. So you might as well give it a go. Okay, the final approach, which is kind of maybe obvious, but it's definitely something to consider as well, is to crowdsource training data, or at least part of it. So basically, you can just use something like Amazon Mechanical Turk, and you ask human raters that this is the task, these are the inputs, what would be suitable out for these inputs. And this is very flexible, you can apply it to any task. But then the downside, obviously, is that this is not a very scalable method, and it might get very expensive if you need to crowdsource a lot of training data. But still, like we discussed last week, that, for example, these text editing methods, they tend to be very sample efficient. So in these cases, crowdsourcing might actually be a viable option on how to do the data collection. And this is something I've also seen in my own work. Also, like I mentioned earlier, that when you do heavy pre-training, this also will make your method more sample efficient, and then crowdsourcing might become viable. And maybe you have some automatic training data, it might, or automatically generated, it might still make sense to crowdsource at least a bit new, more high quality training data, so that then you can first pre-train on this sort of silver data, and then you fine-tune on the crowdsourced gold data. Okay, one sort of challenge with crowdsourcing specifically related to NLG is that often the NLG tasks, you have many possible outputs or many ways to express the same thing. And then different annotators or raters may have different preferences on how do they express things. So you end up getting very inconsistent data. And then the model kind of ends up learning the rater preferences rather than task. And it might get confused when it sees sort of inconsistent outputs. And like what you would normally do if you're doing crowdsourcing for something like a classification task, is that you would take some kind of majority vote over the rater outputs. But here, obviously, it's harder to do. Like, how do you average the outputs when they're all sequences? Yeah, in any case, this is definitely something to consider if you have resources. So the next topic is around evaluation. And this is, of course, something that you'll need to do also when you, like, if you don't want to deploy your model or productionize, but you'll need to evaluate in any case. But I would say this becomes especially important when you want to productionize, and you kind of the evaluation metric isn't given, but your task is just to make the model as useful as possible. And then the question is, what evaluation metrics should you use? So I'm going to present a few possible evaluation metrics. But before I do that, I kind of to activate you a bit. So I'd like to also, so we're going to be using the breakout rooms in the seminar session. So I wanted to give it a quick try. So I'm going to describe this task, and then we'll do very quick, just maybe maximum 5-minute discussion, and then come back together and discuss some of the things that you've thought about. But okay, here the task is about designing evaluation, and the task is the following. So now you've trained this grammatical error correction model, or you will be training those. And let's say that this turns out to be like super great, that this is the best grammatical error correction model that you've ever seen. Maybe you did it for Finnish and you haven't seen a good Finnish grammatical error correction tool before. Okay, and then you decide that I actually want to build some kind of product around this, and it could be something like a text editor plugin or something like this. And now the task is, how do you evaluate that this model does what it's supposed to do? Or first of all, before you launch the product, and then after you've launched it, what more can you do after that? Okay, so thanks, many great answers, and I think you covered a lot of the stuff I'm going to go through next. But so let's move on. So first of all, a common issue in designing evaluation is that usually in NLG there are many ways to express the same thing. So it's not like a classification where you have a fixed set of classes. It's easy to just compute some kind of accuracy, but now you have many ways and you still need to come up with some sort of metric. So some existing metrics, one of you mentioned perplexity, then these n-gram based metrics are very common. There's a model-based metrics. Okay, so let's take a look at each of these quickly. So, but before going into these metrics, regarding terminology, so this can be, at least for me, it was a bit confusing when I entered the field. So the same thing is often referred by different terms. So, okay, input is also referred to as source or the source sentence. Model outputs or the predictions that your model make, they're also sometimes referred to as hypothesis or candidate. And then finally, the targets are sometimes called references or called outputs or called sentences. So this is just when you read the literature, it's good to know these different terms. Right, so perplexity, it basically tries to measure how likely are the test sentences under the model that you've trained. And it's this kind of geometric average of the probability. This probability is factorized into like token level probabilities. I would say the most important thing to know about this, like many of you probably already know, is that because of the inverse, the smaller is the better. So 1 is ideal and it's not bounded. This has some serious limitations. For example, if you have different vocabulary between different models, they're not very comparable in terms of perplexity, but it can be still useful. Like if you, let's say you compare different model sizes and you use the same vocabulary, then you could use perplexity as a measure. And it's often used specifically in applications where you have this kind of prefix language model, something like GPT-3, that you just want to measure how well does it predict the continuation of a sentence. What I would say is a more common metric in NLG generally are these n-gram based metrics. So perhaps the most common is blur. So this has been developed from machine translation, and the idea is that you first split your model outputs and the targets into n-grams, so into sequences of something like 4 tokens, overlapping sequences, and then you compare how well do these n-grams match between the model output and the target. And blur computes something like modified n-gram precision. We won't go into the exact definition, and this is still used very actively, but it has been also found out that specifically for machine translation that it was developed for, it's not a great metric for differentiating methods that are already doing well. So it's maybe good to tell a bad method from a good one, but if you have 2 good systems, it doesn't correlate too well with human evaluations of what is a good translation. Another bit similar metric is called Rouge, and this has been developed for summarization, where it's not so much about precision, but it's more recall-oriented metric. And then I just want to mention a third one called SARI metric. which also splits the the outputs to n-grams. But what makes it different from Bleu and Rouge is that it also considers the input. So it uses the input to determine which tokens or n-grams were kept or deleted or inserted, in contrast to the input, and then computes scores for these three aspects differently and averages them. And this is very nice for something like, for example, text simplification or style transfer, where the input and the output overlap very heavily. And finally, I want to mention just the standard accuracy. So how often is your model output exactly the same as the target, or exactly the same as one of the targets in case you have many targets or many references? And obviously, this won't be suitable for things like maybe things like summarization, where you have multiple, like you have so many different ways to summarize a paragraph. But for some easier tasks that are fairly unambiguous, for example, grammatical error correction, it might be sometimes useful that there's maybe not so many ways to fix grammatical errors if there are not too many. But of course, this wouldn't capture things like, let's say you have 2 grammatical errors and then your model corrects only one of them, you would get a score of 0. So even there, it's not ideal. Okay, then this is sort of simple heuristics. Then some model-based metrics. So BERT score is one fairly popular one, which is a few years old. Here, the idea is that rather than comparing the tokens directly, you compute contextual embeddings using BERT for the output sentence or for the reference and the candidate. So the model output, and then you compare these embeddings. With the idea is that this would be a softer metric that which would capture things like synonyms and give them higher scores rather than just giving them a score 0 if they're not exactly the same. And the idea is that, okay, so you compute the embeddings for each of for each token, and then you compute the matching between the embeddings, and then a score based on this matching. Okay, another model-based metric is called BLERT, which is also a fairly recent one. What makes this different from BERT score is that this is a learned metric, in the sense that the previous one was using a fixed or frozen BERT model that you don't fine-tune or anything, but now you actually fine-tune also the model or the metric. So this doesn't make it useful in cases where you don't already have some kind of, or basically what this requires is that you need to have some outputs that are already rated by humans, and then you fine-tune the model to match the human ratings. So this allows you to get more accurate ratings or more accurate automatic scores, but you need this kind of seed set of human ratings to tune the model on. The idea here is that the model takes input where you just concatenate the target sentence or the reference and the prediction, and then you train this model to output the score. And in addition to fine-tuning, in the paper they propose various types of pre-training approaches. So they generate some sentence pairs via round-trip machine translation, meaning that you take a sentence, you translate it into some kind of rich language, and then you translate it back to the original language, and this gives you a paraphrase of the original sentence, which should roughly have the same meaning. Then they do some further corruptions, like maybe drop some words, and then these pre-training examples, they train the model to recover their, for example, Bleu score or BERT score. So finally, as you mentioned already earlier, it's important to do human evaluation. And I think this is really, like, you cannot skip this part if you want to build a good system. Even in academia, often these days, if you try to publish on, let's say, style transfer, reviewers would often ask that you need to do human evaluation, because some of these automatic metrics are sort of easy to game. So you can fool yourself by just saying that, hey, I have a great Blur score, But then it turns out that, for example, if you just predicted the same output, if you just copied the input, you might get a very high blur score simply by doing that. And an advantage of this human evaluation is that you can ask different aspects, measure different aspects regarding the goodness of the outputs. So some common aspects are things like adequacy or fidelity. So how sort of factually consistent is the output to the input? For example, in machine translation, does the output convey the same thing as the input? Fluency and grammaticality. Finally, comprehensibility. So even if your model output is grammatical, it might still be expressed in a non-comprehensible way, which is not great. Okay, and final aspect around this is that when you design your human evaluation, there are many ways you can do this. So it can either be single-sided, so you just show a model output to a human, and then you ask how good is this with respect to, for example, the above three aspects. But often it can be easier for human raters to do some kind of side-by-side evaluation that you show, for example, the outputs of two different models, and then you ask which one of these is better. So this goes back to also what we talked about Turing test in the first lecture, that where the human, you could also do this against the target, like some human created target sentence, and then the model output, and ask which one of these is created by human or which one of these is better. And if the humans can't tell the difference, then it's probably a sign that it is a pretty good model. Right, and then the final class of metrics, well, I call these here user engagement metrics, but basically what I refer to here is all kind of metrics that you can measure based on how people actually use your system. And so what I mentioned in the previous slide, this human evaluation, that is something you can do already before deploying your model, but this is something you do after deploying your model. So you can measure some standard metrics like how many daily active users, like do people actually like using your system? That's probably a sign, reflects like how well the system works. But then you have these, what we already discussed. So you could measure things like how often do people accept the suggestions that your model has made? Or you could measure some more indirect things, like if you build a dialogue system, you could measure how long are the dialogues on average, which can be tricky on the other hand, because on one end, if the dialogues are long, it maybe suggests that the tool you build is kind of engaging and humans like to use it. But on the other hand, it might also be a signal that people don't get the thing done that they want to get done quickly, but they need many turns. So it could be also a negative thing. But so there are many ways to do this. Just before we go on break, let me give you one concrete example how we use this with this Rappler generation that I mentioned earlier, that I didn't have time to cover in the first lecture. So we built this web tool, like I thought, and this tool has a functionality that you can ask the tool to propose you the next line. And once you do this, what you get is a set of candidate next lines that we have scored with the algorithm. So each of these lines comes with a score of how well does the algorithm think this fits to the prefix. And now we ran a short experiment where we shuffled the order. So we didn't order these suggestions based on the scores. And then what we can do with this is that if human then the user selects, let's say, the fourth example, then we can elicit preferences that probably the person read at least the three first. Maybe they didn't read the last two, but we can infer that the user prefers D over A, B, and C. And now, given that we have these scores for the different lines, we can also measure is D actually better than A or B and C with respect to these automatic scores. And we did an analysis where we kind of took these automatically elicited preferences, and then we measured what's the score difference between these two sentences. And what we found out that the larger the difference between two sentences, the more likely the human is to select the one that is preferred by the algorithm. So this is kind of a signal that the automatic score that we have is kind of capturing something of the human preferences. Okay, let's maybe go forward. We have quite many things still to cover. I'll try to speed up a bit. And speaking of speeding up, so the next topic is how do you speed up your model? So inference, meaning the prediction. How do you make the prediction step of your model once you've trained the model faster? And this is yet another thing that's, at least in my experience, is a bit different in academia. So often, like, if you look at papers, I mean, this doesn't apply everywhere, but often training is the bottleneck. So that's the slow part. And when you have tight resource constraints, you care about the training time more. Whereas if you work for a big lab, maybe you have a lot of resources, you can parallelize the training effectively. So it's not that big of a bottleneck. Whereas if you want to serve the model to, let's say, millions of users, you want to run the model in real time, then latency becomes very critical, and you need to be able to run inference very fast. Of course, depending on the application. But then let's say you're faced with this situation that you need to serve the model to a large number of people with a very low latency. So how do you go about optimizing the model? And now this, of course, it's not just specific to NLG. So you may have come across these concepts before. But so to discuss what are some of the approaches here, I recently came across this tweet by Jan LeCun, who's the chief scientist at Meta. And so he wrote, so somebody wrote that like the race in AI should be towards fewer models with fewer and fewer parameters for given performance. And he commented that while there are a few scientists training in practically large models, there are infinitely more engineers using distillation, pruning, quantization, and architecture optimization to get the same result with smaller and deployable models. So I think he provides quite a nice summary on what are the common techniques used for making the inference time smaller. I would, however, maybe add one technique here, which is precomputation. So let's go through next of these different approaches of how do you optimize the inference time. So first of all, precomputation, here the idea is that if you want to serve your model in real time, you could pre-compute the model outputs for a large number of possible input and store them in a lookup table or in a database so that you can just super fast look up what's the output for the given input and serve it to the user. You don't need to rerun any of the computation. Okay, this can be useful also if you want to combine your model with some kind of filtering step. So you want to run maybe some expensive filtering to make sure that there's not some kind of problematic content or hallucination or things like this. But on the other hand, this has some serious limitations. Most importantly, like often there's a very long tail on the distribution of possible inputs that the users may provide. And also, like over time, the distribution of inputs may change. So there might be some temporal drift that makes your lookup table stale. Just to give you a concrete example, here's a quote from one of Google's VPs. We see billions of searches every day, and 15% of those queries are ones we haven't seen before. This is, at least to me, it's quite pretty mind-blowing that of all the possible queries that a big search company like Google receives, almost every sixth of them is something that you haven't seen before. But you still need to be able to provide a good answer. So if you just relied on a lookup table to efficiently produce the answers, you would you couldn't answer every sixth query. Okay, another downside of this approach is that let's say you come up with a small improvement for the model, and now you've pre-computed this gigantic lookup table. You would need to pre-compute the whole lookup table again if you want to update your model, which might not be practical, especially if you want to update your model often. Okay, in any case, this is something that might work for some applications quite nicely. So the next technique, and I think at least in my experience, this is one of the maybe the most important technique that's often used. So this is called distillation, and here the idea is that you have some large teacher model, and you try to distill the knowledge learned by the teacher into a smaller and more efficient student model. And how do you do this? So you take some large data set of unlabeled inputs, and then you run your teacher model to produce outputs for this large data set, and then you train the student model on this resulting sort of pseudo-parallel data set. So this allows you that maybe your original data set is not too large, but then you run this teacher on a much larger set of inputs, and that helps the student learn the kind of the knowledge learned by the teacher. There are two different ways to do this. You can do either soft distillation, which is sort of the more fine-grained approach, and which is how this was originally proposed in one of Hinton's papers, where you try to match not just the kind of the coarse-grained output, but actually the distribution of the teacher model. So in context of sequence generation, you try to match what's the distribution of each token. Whereas in hard distillation, the idea is that you just try to replicate the output of the teacher model, just what are the tokens and not what's the distribution of tokens. And the hard distillation, of course, it's quite a bit simpler to implement because you just create a new data set by running inference with the teacher model. And I've still found this often to be quite effective. And this is also related to what we talked about self-training, but here you're not training the same model again, but you're training a smaller model with the predicted outputs. Okay, the next technique, and I won't be going into much detail, but just to give you an idea what it means. So pruning, here the idea is that once you've trained your model, you can trim some low magnitude weights, so some weights that are close to zero. You can just make them zero in order to compress your model or make it sparser, and which would also make inference faster, at least in some cases, depending a bit on what sort of architecture you run it and so on. Quantization, this means that you use some lower precision. For example, you use 8-bit floats rather than 32-bit floats to represent your model weights. And this is also a way to make the model more compressed, so it takes less memory, but it also makes it usually faster to run. There are different ways you can do this quantization or training, or you can do it after training the model. But yeah, this is something to look at. And finally, what LeCun mentioned in the tweet was architecture optimization. What I think this refers to is to simply varying the model hyperparameters to find a good trade-off between the model size and the quality of the outputs that you get. So you can vary different things like the number of layers or some hidden sizes and so on. And you can either do this manually, or you can use something like neural architecture search to automate some of this process. One thing I haven't actually used myself, but talking to people who are more experienced in this area, they've thought that, for example, for TensorFlow, you have a specific profiler which makes this process much easier because you can actually find the bottlenecks in your model architecture, so you know what are the hyperparameters you should be optimizing. All right, so that's it about inference speed. So let's next move to hallucination mitigation. So hallucination has come up several times in the previous lectures also, and this is an area I find quite fascinating myself. So how do you make sure that the outputs of your model are factual and don't contain any embarrassing facts? And this, especially for natural language generation, this is like if you're training a classifier, it's maybe not so bad if your model sometimes predicts the wrong class. But if you are training an NLG system and your model produces some totally invented facts or some offensive content, it can be a really big problem. So So you really need to make sure that your model kind of doesn't produce some unreliable outputs. So how do you go about this? Or actually, before going to, just to give you some ideas. So in this laser attacker paper that I mentioned in the previous lecture, we analyzed a bit what are the types of hallucinations that our sequence baseline, the transformer model, was making, as well as the text editing model. And so you can see that sometimes, for example, if the model encounters characters or scripts it hasn't seen before, then it has no idea what to do, and it can just come up with some words like in the first example. And sometimes the models start repeating stuff if it's not trained well, or if there's not a lot of training data, or sometimes just come up with some very, very nonsensical outputs. Okay, so how do you avoid this? Let's go through few different approaches. One that I found to be very effective in practice is that often when you see a hallucination or something kind of what's unwanted, usually there's some training data that has the similar phenomenon going on. And if you just clean up your training set, you can get rid of this. So this is usually the thing I do first if I see some problematic hallucinations. Try to find, filter the training data. Is there something similar going on there? And remove just those training examples. The second thing you can do is to try to control the output vocabulary of your model, which is something we do, for example, in text editing. So we don't let the model output any kind of text, but we sort of restrict it. This might not be applicable to all kind of tasks, but in a task that are sort of more controlled and don't require so heavy rewriting, this might be a valid approach. And finally, there's a lot of work in the area of question answering and also in question generation. And recently there have been few works that kind of combine these lines of work into tackling hallucinations in quite interesting ways. So let's take a look at one example. So 2 papers just to mention here, and we'll take a look at the first one where they use this idea for summarization. Okay, so here the approach is that first of all, you have a long source paragraph, and then your summarization model produces a summary for this source paragraph. And now you want to detect, does this summary hallucinate? So does it predict some factual inconsistencies with the source? And how you do this? First of all, you can extract a set of possible answers, both from the source and from the summary. Just find something like entities or some noun phrases. Then what you can do is to generate questions for these possible answers for the summary. And then, okay, so this is the question generation part. Then you can run your question answering model. So this is the question, this is the sort of the source paragraph. What's the answer to this question? And now if you get inconsistent answers between the summary and the source to a given question, that would be a signal that now there's some kind of factual inconsistency or hallucination happening. And then you can sort of average the number, compute something like the average number of consistent answers to these questions to get some kind of score for how much your summary contains hallucinations. Okay, so this is quite an interesting and I would say smart way of doing hallucination detection. All right, and finally, so the final part I want to talk about is ethical considerations, and this is, I would say, this is quite a hot topic. So there are a lot of debates on Twitter, and it's also a very active area in academia. There's a lot of research going into this, and also even if you like many conferences have adopted these guidelines that you should discuss something like the broader impacts of your work or some ethical, you have to include a section on ethical considerations. So this is definitely something to learn more about. So, and there's a wide range of possible ethical issues that previous works have outlined. So there are things like bias, often these NLG models or NLP models in general, they pick up whatever biases there are in the training data, or these biases can result also from even from things like the model architecture. And there's problem with misinformation. So this is related to the problem of hallucination, that these are not always producing factual outputs. But on the other hand, also these can be maybe sometimes sort of weaponized to spread misinformation more effectively. The third type of ethical issue that I personally feel kind of that I'm sort of a bit worried about is how that you can use these NLG methods for spam. So for example, there is even some work on review generation. So the worry here is that kind of the whatever reviews, I mean, already there are things like paid reviews, but these might become more and more automatically generated, especially given that the outputs of these large language models, it's actually very hard to tell them apart from human written text. Leaking private information. So these models are good at memorizing stuff they've seen in training data, and it can be sometimes possible to kind of tease out these. So if your training set contains some private information, you might be able to tease it out from the trained model. And finally, environmental costs. So like how much CO2 these models, just training these models produce, because especially these large models, they actually require a lot of compute to train. And there are many more issues, but so this would deserve its own lecture. I'm now only going to focus on one of these bullet points, but we will have a separate seminar session where we talk about this more broadly, as we're going through 2 papers in this area. But so I'm going to say something about the bias because it has some connections to my own work. So before talking about my own work, it's just kind of the common example that you see related to bias is gender bias in machine translation. So some languages have gender neutral pronouns like Finnish. So you often see examples like this, like if you okay, so let's just go. So you might see like the model outputs, he's studying computer science while she's studying computational linguistics. So in this case, of course, there's no one sort of manually making these associations, but this is something that the model picks from the training data. And these might kind of reflect let's say what's the majority of students in the society, but they might sometimes these biases are not even reflective of the kind of the society, but it's just reflective of the data set that you happen to use for training this model. So in that sense, it's important to pick your data set correctly. But even if these were like reflective of the society, even then you might not want to sort of propagate these biases to your users, but you would like to control them in some ways. And there's a lot of work on how do you do this kind of controlling or de-biasing your methods and things like this. Actually, I just tried, like if you try a single sentence, these different machine translation systems, they might actually show you like the 2 possible translations. But of course, when you combine many of these, you would get an exponential number of different combinations. So then it becomes sort of a UI problem. How do you present these possible translations? Okay, but there's a very nice paper called Societal Biases in Language Generation. So this is a survey paper of the work in bias in NLG. And I just wanted to show this table to highlight that, first of all, this is a very active research area, as I mentioned. The most common aspects that people look in this field are, at least assuming the sample of papers that this survey used, it's gender bias and race bias. And another interesting task to look, or aspect to look, is on what type of NLG tasks are these different kind of demographic biases studied. So most of this work is in the context of machine translation, like we saw in the previous slides, or autocomplete here refers to the prefix language modeling task where you are asked to complete a given sentence, and dialogue. So these are sort of, especially autocomplete and dialogue, these are sort of open-ended tasks where there's not just a single correct output, which makes these models kind of more susceptible to bias because there's no clear direction where they should go. On the other hand, I think if you, let's say you train something like grammatical error correction bias, grammatical error correction system, these type of systems would be less susceptible to bias, although of course it can be a danger there as well. But you see here the category of rewriting, there's much less work in this area. And I think this is like the existing works here are something like when you are inflecting a word, in some languages, the gender might be kind of, you have a different inflection for different gender, and the model might make mistakes in this regard. But okay, so going to my own work, we have this paper on sentence fusion, and here we did a short analysis of how often does the model get the pronoun right when it's performing pronominalization. So when the model is replacing an entity name with a pronoun. And okay, it does seem to get it right pretty often, but it does still make mistakes. And if you look at this confusion matrix, you'll see that, for example, the model is more likely to confuse when the correct pronoun would be she. The model is more likely to mix it with he than it is to mix he with she. So this would be one type of bias visible here. How do you avoid this kind of biases? Well, I mean, one thing I mentioned already is that maybe you don't actually want to delegate the task of choosing the pronoun to the model, but you'll just ask your model to choose whether it should produce a pronoun here, and then maybe you have some kind of external knowledge base where you can look up the gender of the person and then choose the right pronoun based on that. Okay, just to give you one idea, but as I said, there's a lot of work going on here. If you're interested, here are a few papers related to bias or ethical issues around NLG methods and NLP in more general, and two of these we're going to discuss in the seminar session.